The problem statement from Gate Physics 2014 reads as follows. The current gain of the transistor in the following circuit is beta DC equal to 100. The value of collector current IC is dash milliamps. We have been given a circuit which has a BJT, an NPN BJT, and some resistors and some power supplies with some blocking capacitors, and we need to find the value of the collector current. This is a numerical answer type question, and once we find the answer, we'll fill in the blank here. Before we try solving any questions relating to BJT, we ask ourselves a few questions. The first is, what is that? Which BJT is it? So which BJT is it? Is it NPN or PNP? So this, as it clearly visible from the symbol, that this is an NPN symbol. Second, we ask ourselves whether the BJT is in forward active mode or not. So what is the forward active mode? Forward active mode is when collector bias is reverse biased and emitter bias is forward bias, right? So we'll see that only when this is active, then only our formula that beta DC equal to IC upon IB, all these formulae are valid only when the BJT is in forward active mode. So we must verify that. Now this question is silent whether this is in forward active mode or not. We'll just assume that. Okay, so let's move ahead. And since this is a DC analysis, these capacitors can be ignored. These capacitors are used to block just the DC voltages, so we can effectively ignore these capacitances here. Let's get a brief view into the working of an NPN BJT. On the top left here, you have an unbiased NPN BJT, and if we bias it in this following manner, that NP is forward biased, base emitter is forward biased, and base collector is reverse biased, you will get a large amount of electrons injected into the emitter. From the emitter to the base, a few will recombine, while the majority of them will get collected at the collector, and the currents will obviously be in the opposite direction of the flow of the current. And due to the application of bias, the Fermi levels shift accordingly, and you can see a large amount of electrons coming in, very few recombining, some holes also diffuse back, while the most of the electrons are collected. Mathematically, these can be represented as this first expression is nothing but the Kirchhoff's current law, IE equal to IC plus IB. Beta is the current gain, which is collector current over base current. Alpha is the collector current due to over the emitter current. Alpha is usually very close to unity. Now I just told you that here in this diagram is base emitter is forward bias, so collector base is reverse bias. However, there are 4 such configurations, and the most commonly used, when I told you base collector reverse, base emitter forward, is we called this at the active or the forward active region, and you see is this region between the points B and C. This is the forward active region. The other region is forward for when both the PN junctions are forward bias, and this is called the saturation region. You can see in between the points A and B. Here the transistor is behaving more or less like a resistor, because you see I is direct proportional to V here. A third region is when the base collector is forward but the base emitter is reverse. This is called the reverse active, which is not shown here. Essentially, the emitter and collector have reversed their roles. And finally, when both the PN junctions are reverse bias, and this is the cutoff region, which you can see here in this grayish region. We do not operate beyond VCE because that device tends to break down. So you can see after the point C, we do not usually operate. Now this is called the output characteristics. This is IC versus VCE, and you can see as we increase IB, IC increases, because we know that beta equal to IB upon IC. You know that beta equal to IC upon IB, sorry. So IC is nothing but beta IB, beta being a constant. As we increase the IB, IC should increase. Getting back to the problem, we were given beta equal to 100 in this circuit, and we were required to find the collector current IC. IC is shown in the figure, as you can see. And let's also label the nodes voltages. Now, as step 1 is we'll apply KCL at node VB. So let's do that. The incoming current at node VB, as you can clearly see, is just this current I. So I'll write I equal to the outflowing current, which is IB here, IB, plus this current flowing through capacitor. Since this is DC analysis, no current will flow through the capacitor, so this is 0. So I equal to IB is our first expression. Now step 2, what we'll do is we'll apply KCL at node VC. So let's do that. Again, you see the inflowing current is, this is the current I naught. This should be equal to the outflowing current, which is I. You see this current I, plus again this capacitor, no current will flow in DC analysis, so plus 0, plus this outflowing current, the collector current IC. Now we know the value of I equal to IB, so I naught will become IB plus IC, and we also know that IC equal to beta IB, so this will become beta plus 1 times IB. This I'll call as expression 2. Now what we are going to do is that we are going to apply KVL across the green line that you can see on your screen. So KVL along green line, let's do that. So I'll write 12 minus I naught times 3k minus I times 150k minus VBE minus IE times 3k equal to 0. So let's go through this. So 12 minus I naught times 3k, this term, minus I times 150k, the drop here, minus VB, the drop here, and finally IE times 3k, the drop here. Now we know from expression 2 that this is beta plus 1 IB. We know this is IB from expression 1, and we know IE is nothing but beta plus 1 times IB, and since we have assumed a forward active mode, VBE will be 0.7. So now let's collect all the IB terms on one side. So it will be IB. So if you see the first term here, that will be 3k times beta plus 1 plus 150k, the second term, plus again beta plus 1 times 3k, and this will be equal to 12 minus 0.7. So if you put the value of beta here, so this will be 303k plus 150k plus again 303k, this will be 11.3, and this will give IB equal to 11.3 over 756k, and thus IC, which is nothing but beta IB, this will be 100 times 11.3 over 756k, which will come out to be 1.495, and let's round it off to 1.50 milliamps. So IC is 1.5 milliamps. Now that we have obtained the collector current to be 1.5 milliamps, let's just confirm that this device is indeed in forward active mode. So for that I have just labeled the 3 nodes of this BJT, and we'll try to confirm that whether the first assumption of forward active, the base emitter, is forward bias. So we need to find out the voltage for VB and VE. We'll see if this assumption is correct or not, and also we'll try to find out whether the base collect junction, which is reverse bias, which is the second assumption for forward active mode. For that we need to find the voltage VB and VC. So let's go ahead and let's just first find out the voltage VC. In order to find the voltage VC, I'll apply Ohm's law across this 3 kilo ohms resistor. So I can simply write 12 minus VC equal to 3k times IC, which is 1.5. So I get VC is 12 minus 3k times 1.5 milliamps. So I'll get 12 minus this is 4.5, so this I get as 7.5 volts. So VC I have got as 7.5 volts. Okay, now let's obtain VB. So how do we obtain VB? VB is nothing but if we apply Ohm's law across this 150 kilo ohms resistor, note that the current flowing here is IB, right? So I can simply write again that VC minus VB is equal to IB times 150k, right? And from that I'll get VB equal to VC minus, the value of IB is nothing but IC upon beta. So IC is 1.5 milliamps over 100 times 150 kilo ohms, right? So the value of VC is 7.5. This will come out to be 1.5 times 1.5, that's 2.25. So this will value come out to be 5.25 volts. So we have obtained VB as 5.25 volts, right? What's left? The left is VE. So VE, how do we get? If we apply Ohm's law across this resistor. So let's do that. So this will be VE minus 0 equal to 3k times IE. Now this is just a simple check, so I can assume IE is approximately equal to IC. So this will be 3k times 1.5 milliamps. So this will be 4.5 volts. So I have obtained VE as 4.5 volts. Now let's check the this junction, VBE PE junction. So this is P. Note that base is P type and emitter is N type. So base is at higher potential, it's a 5.25 as compared to the emitter, which is 4.5. So this is 5.25, this is a 4.5. So clearly this is forward biased, right? Hence what I can say is that our assumption that, so this is true, our first assumption is true. What about the second assumption? Let's check that also. So we saw that this is okay. Note this is N type and this is P type, right? So we see that the N type collector is at 7.5 volts, right? We see that this is at 7.5, this is 7.5, well this is a 5.25 volts. So you can clearly see that the P terminal for this junction is at lower potential, is at 5.25 as compared to the N, which is 7.5. This implies that base collector is indeed reverse biased. So we have obtained that the base collector junction is reverse biased. This assumption is also true. So both our assumptions are true, hence the analysis that we did was correct. And so our answer is indeed 1.5 milliamps. Now please note that you don't always have to verify these assumptions. It's just a good practice that we do that for the sake of completeness. So yeah, our answer is 1.5 milliamps. That's all. Thank you for listening.